So, this is the second lecture, and today I will be speaking on this topic, and this is much easier than what you have heard of, and my main purpose will be to give a feelings for the spectroscopy and how the theory develops and how the theory is developed to match with the experimental data. So, you know that we often start with the hypothesis, and then we see that it is not enough to explain the experimental result and then change the hypothesis. So, that kind of discussion today I will do so that you can have a feelings for the spectroscopy. So, this will be based on FTIR spectroscopy. This is the energy diagram. If you know this one, that this S0 and S1, they corresponds to electronic state, ground state, excited state, ground electronic state, first excited electronic state. So, in that electronic state, you will have several vibration and energy levels, like this is V is equal to 0, V is equal to 1, 2, 3, 4 and so on. So, several vibration energy levels under the S1. These are under the S0. So, in between these vibration energy levels, if you zoom it, then you will see that several rotational energy levels. So, this is the rotation, this is the vibrational energy level 0 and this is the 1. So, with 0 you have several associated rotational energy level 0, 1, 2, 3, and for the excited vibrational state you have several rotational energy level. So, when you discuss about the transition among the rotational energy level, then this is called rotational spectroscopy or microwave spectroscopy. When we discuss the transition between the vibration energy level, say from here to here or here to here, then this is called vibrational spectroscopy. When we talk about the transition between the two electronic state, then it is called electronic spectroscopy. So, today we are discussing the vibrational spectroscopy. So, to start with, we usually start with the simplest molecule, and that is the diotic molecule. So, that means you have two atoms, and these two atoms are vibrating. So, this means this is vibrating like this, vibrating along with a mean position. So, this is the stable position, and that distance between the two atoms is known as equilibrium distance, that is the bond distance. So, at the beginning, and you see 1676, Robert Hooke, he imagined 1676. So, long back, Robert Hooke, he imagined that this vibration is like a spring motion. The spring is vibrating. So, he imagined that, so like is a spring, this is spring. So, this spring is, you stretch, like you have diotic molecule, this is one atom, this is another atom. So, better we start with here. So, diotic molecule, this is one atom, this is another atom. So, this is the stable position, this is called R equilibrium, bond distance. Now, when you stretch it, then that is not a stable position. That means the system has more energy. So, the system got more energy, and the the stretched one is this one. When you compressed it, compared to the stable position. So, then again system has the same amount of stretching and compression will give you the rise of the system energy same amount. So, you have the compressed one, you have the stretched one. So, stretch more, energy will increase more, compress more, energy will increase more. So, this is how the potential energy surface is constructed. So, spring motion, so Hooke's compared this one with the spring motion. So, then spring motion, this is known. The force acting on the system is minus K R minus R equilibrium. So now this R is that if you think of any scenario, say you have this one. So say you are thinking of stretched one. So from here to here is the R. And what is R equilibrium? R equilibrium is a constant value. So from here to here, that is R equilibrium. This is R equilibrium. So R minus R equilibrium. So R is bigger minus R equilibrium. This is positive quantity minus. So what this minus says, that it is attraction force is working on it, because two atoms are forcibly separated, so they will try to come close. So in opposite case, say here, opposite case, this is the R in the stretched condition. And equilibrium distance from here to here, this is R equilibrium. So R minus R equilibrium because minus plus. So that means now this instead of attraction, it will be repulsive. So this is the meaning of the R. So energy for this whole things, this profile indicates that it will be a parabol. So that is that half k x square. Okay. So this is a simple harmonic motion. Why it is simple harmonic motion? Because you have a molecule like this. This is stretching, same amount compressing, this increasing the same amount, increase of energy. So more stretch, more compress. So this one says a parabol. So this means you stretch more, compress more, nothing happens, just increasing. This is taken from internet. If somebody has still a problem, then you can think of this way. So you see this atom is vibrating and then vibrating between these 2 points. So it is stretch, this is compress. Here there is some problem. Anybody can tell what is the problem? I have taken it from the.
Two atoms are not.
Why? How it will go? So it is taken from Wikipedia. What is the problem here?
The sizes of the atoms are not same.
No, we are talking about HCl molecule. So its sizes should not be same. Yes, the heavier one should be fixed and the smaller one should be. So this even after noticing, I still put it because the Wikipedia, many people think Wikipedia is like a Bible. So it is not. Internet, one has to be very careful when you are blindly taking figure from internet. So it is always good to rely on the website which is developed and maintained by a professor from a big university, like a Caltech or American top universities, or some well-known scientist. Not that somebody is putting, because that person, he doesn't know about this one. He just because no scientist had drawn this GIF file, no, somebody else has done. So he has no feelings that which one should be fixed and which that smaller one should go. So the oscillation, we are talking about the vibration. So there will be oscillation frequency. The oscillation frequency in Hertz is 1 by 2 pi by k by u. And since this spectroscopy we discuss everything in wave number, so you have to divide it by c and then it will be in a wave number. So oscillation frequency, this is omega bar. Whenever bar comes, that means it's wave number. So 1 by 2 pi c k by mu, that reduced mass. So now in case of Schrodinger equation, we have to solve the Schrodinger equation to get the energy levels. These are the energy levels. So these are the energy levels we have to get. That energy levels comes out of the solution of the Schrodinger equation. So this is the Schrodinger equation. In that equation, you know, potential energy, kinetic energy, and this is the energy that you will be replacing. So there we have seen in the last slide that the energy term is this one. So this we have to replace there. This we have to replace there. And then solution of the Schrodinger equation gives you the energy levels. First gives you the expression EV, capital E, V stands for vibrational. So E in joules, V plus half H omega OSC. So this is in joule, you have to divide it by HC, then it will be in centimeter inverse. So if you divide it by HC, then omega by C, that means omega bar. So you have the expression V plus half omega bar. So this is the energy level expression. And so now let us see how the energy levels are. So first energy level, ground state, V is equal to 0, V is equal to 0. If you put V is equal to 0, then you have half omega SC. So V is equal to 0, V is equal to 0, there is energy level. What is the value? Half omega bar OSC. Now V is equal to 1, V is equal to 1, 3 by 2 omega OSC. So V is equal to 1, 3 by 2 omega OSC. So you can keep on calculating and get the energy levels, vibrational energy levels in a diatomic molecule. What you are getting? Vibrational energy levels in a diatomic molecule. Why do we need vibrational energy level? Because we have to think of transition. Transition will take place between the two energy levels, following some selections rule. So between the two energy levels means we have to first know what are the energy levels. So we get the energy levels. And then when you think of the transition, so we need some guidelines. It's like you are in BSc first year, where you will transit, whether second year or third year or MSc first year or MSc second year, there is a guideline given by the UGC. So guideline is that you can change by +1. So BSc first year to BSc second year. So these guidelines is also given by the Schrodinger equation solution. So delta V plus minus 1. So plus 1 means it is the absorption, minus 1 it is the emission. So what does it mean? It means that we can think of a transition between the two energy level where delta V will change in unit. That means if you think that your molecule is here and you are expecting a transition, so you can think of a transition from here to here. What is the delta V for this? Delta V is final, always final minus initial. So this is +1. Fine. Now I expect that there should be a transition from here to here. Let's see. Delta V is final is 3 minus initial is 0. That means +3. Is selection rule permits? No. So I cannot think. So I can think only the transition which changes by 1 unit. That is shown here. And now where the band will come? Band will come final energy level minus initial energy level. So final energy level minus initial energy level. This energy level is 3 by 2 omega bar OSC minus half omega OSC. So what is the value? 3 by 2 minus half. Omega OSC. ठीक है? So we can expect one band. So this means that this whatever expression we are seeing, if we calculate that a transition from V to V plus 1, first put in the expression V plus 1 minus V plus 1 minus V, then you get omega OSC. So you get only one band, because you think of transition here, omega OSC. If you think of transition from here to here, calculate. This is 17 by is 1. Okay, so that means that this transition so everything is giving in the same position. So every band is coming in the same position. So that means you will see only one band. But in reality, even in the low resolution spectroscopy, then you see the existence of two bands. This is one band and this is another band. This thing we'll be discussing later, but as of now you think multiple band. So this simple harmonic motion of a diatomic molecule is not able to explain the observation, experimental observation. So we have to think why. In this way, this one I am showing you, this is a different thing. This one I am showing you same vibrational spectrum, infrared spectrum of HCl molecule. You see this is also HCl molecule, this is also HCl molecule. But they look quite different. Why? There is a change in the x-axis, there is a change in the y-axis. What is the x-axis change? This is in terms of transmittance. So transmittance 100 and it is coming like this. Usually IR spectrum is recorded in this way. For inorganic chemists, they like this IR spectrum like this, transmission mode. But if you do it in absorbance mode, then the spectrum looks like this one. So this is in absorbance mode. And scale here, this side is 1000. From this to this, energy level increases like this, wave number. And here, energy level is increasing like this. So that's why both this axis and this axis changed. And that's why the spectrum, same spectrum, looks different. So first thing is that you should be used to seeing the axis. Caption, what is that? That is very important in spectroscopy. So this one, you have seen the last time, in last slide, I have shown you that one band like this and like this. So this band was looking quite low resolution. This one, you see, is quite low resolution. So if you do the experiment with a high resolution spectroscopy, then you see this thing, this kind of. So where it is published? It is published in Journal of Chemical Education, 2018, very recent. 2018 is very recent. And this is a very popular journal, Journal of Chemical Education is a SCS journal, it mainly to educate the student. And there, they have published by Johns Hopkins University, published by one group, somehow it deleted. This is reported by a researcher from Johns Hopkins University. Johns Hopkins University is top rank university. So imagine they are doing a work on the HCl molecule, which is supposed to be very traditional one. So what is the beauty of this thing is that whatever data they get out of using the recently developed instrument, that data is the ultimate. So that changes the textbook numbers. So there is nothing like if you work on nano and that is the important one, and if you work on traditional field and that has no meaning. It is not. You see, this is one example. So this spectrum is, you can tell, the highest resolution spectrum so far reported for this molecule. So there, remember, so this is 3500 and this is 2650, and this one is fundamental vibration rotational band of HCl molecule. This is for HCl molecule, and B is the for DCl molecule, that isotope, and this is fast overtone. So they have recorded fast overtone also. So this is the fast overtone, just double of this number. If you see, these numbers are double. So 2200 This is 5800. So this first one. We'll discuss these things slowly. This is just to tell you that. So what we have seen just now in high resolution also, that the spectrum is not just one band, it is much more than that. So where was the problem? Problem was that in harmonic oscillator, that there is no bond breaking aspect. Means you stretch it, nothing happens. Compress it, nothing happens. But it is true that once you stretch above a limit, then bond should break. But this bond breaking incident, a bond breaking fact is now included, and this is included by the PM Morse. So what he did is that Morse, he empirically gave an equation which satisfy this curve. Okay, this is the curve. So what is the difference between the harmonic and anharmonic? Harmonic and the biggest difference is that in harmonic case there is no bond breaking, but which is we should have. Okay, so now in this, so what Morse did, now in this case your energy expression is that considering the spring, the parabolic half kx square, but this one, this must be different, and then Morse gave an empirical equation that if you put that equation, and this is that equation, this energy equation. So this energy equation DEQ means from there to dissociation energy level, equilibrium to dissociation energy level. This is a small constant depend on the molecule. So if you use this one and solve the Schrodinger equation, then in addition to the existing one that already had, you have another term. This is the additional term. In this additional term, you have V, omega E, both are there, and you have an additional one, that Xc, which is called anharmonicity constant. What is the anharmonicity constant? It is the deviation from the harmonic nature. So this deviation from the harmonic nature, the more is the deviation, anharmonicity constant will increase, but it is still a small number. This is still a small number. Okay, so now you have again energy level, so you can find out what is the this E0 value, and remember this is a big difference. Classical approach says that the molecule can have zero vibrational energy level, but you have seen their molecule cannot have a zero vibrational energy level, not even a simple harmonic motion or anharmonic motion. So now you have a different expression, so you will have a different energy levels, and this selection rule is also now relaxed. Earlier selection rule was delta V plus minus 1 only. Now we have many more possibilities, plus minus 2, plus minus 3, almost anything. Okay, so every transition is allowed according to this selection rule. If it is so that every transition is allowed, then it is much more complex. So let us simplify the situation. In that way, as we have discussed in last class, then that what guides the intensity? Intensity is guided by the population of the originating state. So how much is the population? If the population is high, then you can expect, if everything is satisfied, you can expect higher intensity. If population is not there, then you cannot, even if it is allowed, you cannot expect much intensity. So since now delta V is equal to plus minus 1, plus minus 1, plus minus 2 and everything. So let us see that this is V is equal to 0. Let us see how much is the population at V is equal to 1. Just V is equal to 1 compared to V is equal to 0. For that, use simple Boltzmann distribution. So population at V is equal to 1 with respect to population at V is equal to 0. This exponential minus delta E, and here delta E is vibrational. If you think of the IR spectrum, it comes in 3000, 2000, 1500, it is 1000. So we add 1000 for general purpose, 1000. So 1000, that is, but here in this we have to use in joule. So this is in wave number. So you have to multiply by AC. So Hc multiplication. Okay, that is why so many numbers are there. And then Kt. T is in room temperature. So if you see this one, then number of population of n is n at V is equal to 1 is not even 1. You see, it's not even 1%. It is less than 1%. This means that n V is equal to 1 is n V is equal to 0 into 0.008. So if you multiply by 100, that means 8. So 0.8, that means 0.8. So not even 1%. So if you have 100 molecule in this n is equal to 1, 100 molecule at V is equal to 1, then you have 0.8, means not even one molecule. When population is so low, then we don't have to think of any transition from other than V is equal to 0, unless you are increasing the temperature. If you increase the temperature, obviously higher energy levels will be populated, then you can think of. So now what we will consider is that, to simplify the situation, that we will consider only the transition which is happening from V is equal to 0. Okay, no other transitions. So we will be considering V is equal to 0 to V is equal to 1. Now V is equal to 0 to V is equal to 1, this will have a considerable intensity, and for that you first use V is equal to 1 in the expression minus V is equal to 0, and whatever expression comes, that is called fundamental absorption band. So the strong band you have seen, that is the fundamental absorption band. Now next V is equal to 0, we have to consider only the V is equal to 0, V is equal to 0 to V is equal to 1, V is equal to 2, V is equal to 3. So this is 1, this is 2, and this is 3. So V is 0 to 1, this will be the strongest one, this transition is strongest one. Then 0 to 2, that means 0 to 2, this one. This expression will be 2 omega E 1 minus 3 xc, and the third one, this will be 3 omega, it is hidden here, 3 omega E 1 minus 4 xc. This is called fundamental absorption band, this is called first overtone, this is called second overtone, and if you keep on thinking 0 to 3, 0 to 4, 0 to 5, but in reality we see fundamental absorption band and then first overtone. Other bands intensity is so small that we don't see it in reality. Okay. So what we have learned so far is this one. So we had a simple harmonic motion which gives one band. Now we have an anharmonic oscillator which gives you multiple band. Okay. Say for HCl, now with that data, we can calculate the first band, strongest band comes at 2886, this middle of this one, 2886. So the expression was omega E 1 minus 2xc, so 2886 is equal to. Now the second one is, second band comes at 5668. So if you have these two, even if you see the fundamental band and fast overtone, you have two expression, two unknown quantity, so you can calculate the very important oscillation frequency, omega E bar 2990, and as well as anharmonicity constant 0.0174. So apparently this spectrum now not giving any information, but if you know the fundamentals of that spectroscopy, what is the fundamental in this case? The first band, the strongest band, which is known as fundamental band, that expression is this one, and from that spectrum we measure where it comes. So if we equal these two, then we have expression this one, Where the first overtone comes, 5668, 5668, and what is the expression for that? This is the expression. From these two, we get omega E, vibrational frequency, and Xc. And then you can calculate the K value and so on. So this all gives you the strength of the bond. Okay. So we are happy that we have multiple bands, but okay. So another scenario is that if you have a scenario, if you experimentally observe, there is a weak band before the fundamental band, then what is the reason? The reason may be that there is some amount of population from V is equal to 0 get transited to V is equal to 2. If there is a population at V is equal to 1, which we just calculated, it should be less than 1%, but because of the molecular system, because of the temperature, if you have that appreciable amount of population, then you can see a band before the fundamental band. Otherwise, fundamental band should be the first band. And how to know that this is not the fundamental band? Obviously, intensity will be much less, and also this intensity will significantly vary if you change the temperature of the system. If you increase the temperature of the system, then this intensity will significantly vary. So this is known as hot band. Why these things are? Okay, this is known as hot band. So this one I have taken from a so it's gone. Oh, okay. So this is you see this carbonyl band. Okay, so this is carbonyl, and this is a fundamental band, fundamental absorption band. You see the strength. Strength is the area underneath the band is a measure of the strength. And what is the first overtone? First overtone of this one is this one. Imagine the strength. So if this is the strength of the fundamental band, first overtone is this much only. So we don't expect that second overtone or third overtone to be seen. Let it be here. Okay. So what we have learned, that this big band is fundamental absorption band, whose expression is this one. This small band is a first overtone band, whose expression is this one. This expression, if you a bit carefully see, this expression, it contains the oscillation frequency minus twice of Xc. Xc is a very small quantity, you have seen that 0.01, and on the other hand this one is in 1000. So, and where this first overtone comes, double of omega E minus some minus. So ideally if it comes at 2000, where the first overtone should come? First overtone should come close to the 4000. Close because there is some minus, and this minus is very small amount. So this one is say 2200 like this, and you see this is 4400 like this. Okay. So this is a spectrum taken, IR spectrum of CO molecule at 650 millimeter mercury pressure, means less than atmosphere pressure, and 10 centimeter cell. You have used 1 centimeter cell in electronic spectroscopy. This is 10 centimeter cell. Because it's a gas molecule, the number of molecule is less, so you should have a bigger path length. Intensity depends on the path length, that we have discussed in last class. So the fundamental band is seen 2143, and the first overtone is seen 4260, is close to the double of this one. Okay, this double means 4286. 4286 ke jagah 60 minus some amount of that Xc value. That is based on this expression. But this is not the everything, because as I said that we always want to see more. So when you see more using some sophisticated instrument, then you see the structure of this fundamental band. This whole thing is a one band. This is called fundamental band. This one is first overtone. This is second overtone. This one is hot band. So when you see the first overtone band, then you see it is not just a band. It consists of many lines. But our theory doesn't talk about the lines. That means this anharmonic oscillator model is also not enough. We have to even further think how to explain these lines. So if you zoom the lines, then you see this is some lines very consistently with a consistent spacing. Some lines appears. So now our turn is to explain the why the lines appears. Before that one, that I wish to tell you this position. Now we are discussing about we have discussed about the position, whether it will come 2500 or something. Now let us talk about, only one or two slides are there, talk about the intensity part. Intensity part, so intensity is given by the transition moment vector. So what is the transition moment? If you think of transition moment is R, N, M at the two state. So this is the wave function of the N state. N state here is excited state. This is two state. This is M and this is N. So then the transition moment which gives you the intensity, transition moment is psi star N dipole moment vector and then psi M ground state and d tau volume element. A dipole moment vector, you know, he has already discussed dipole moment vector. So the transition moment for it, this one is given by this one. Now we have to discuss this one. So now it is a vibrational spectroscopy. So we have to think how the dipole moment change with the stretching process or compression process. So the dipole moment change means this dipole moment. So this dipole moment change with the stretching process. Before that, let us talk about why a molecule having no permanent dipole moment does not show no permanent dipole moment. If the molecule has no permanent dipole moment, then that molecule is IR inactive. Why? Because this term becomes 0. So intensity is 0. This is a kind of selection rule you are seeing how it arises. Now, if it is a homonuclear diatomic molecule, obviously mu will be 0 and you will not have any intensity. Now, if it is a heteronuclear diatomic molecule, then mu is not 0. And how it varies with the X? So variation of mu with the X is expressed in terms of the Taylor series. What is that? Mu, the variation of mu with X is mu E at equilibrium position. This is a constant term. Del mu by del X, this at equilibrium position into X, 1 by 2 factorial, this and X square and so on. So now we have to use this expression here. This is a very simple thing. So if you use this expression here, then you have the first term. First term is term consisting this constant term. So the term consisting this constant term is integration psi star upper state psi star lower one dx. Next one is this goes out. Why? This is a constant one, d mu by dx at equilibrium, constant one, x remains inside. So this one out and then x inside this one and dx and so on. So this is our expression now. Now in this expression, this one, these two wave function is the eigenfunctions of the same Hamiltonian, and that's why they are orthogonal and they are 0 unless V prime is equal to V prime, this will be 0, this will be 0 unless these are not same. So this term is 0. So what is remaining? The next most contributing term is this one, others will be less contributing. So if you see this term, this term consists of this one and this one. So let us see what is this term. What is this? This is change in the dipole moment with the change in the displacement. So we are talking about this term. So if you plot mu, dipole moment versus displacement, then this is the slope. d mu by dx is the slope. So slope means like this slope one is shown, this is one is shown, or like this. Now you see that how much slope can change from positive, 0, negative. Now important thing is here. So a slope can be 0. If this is 0, means the second important term, first term is 0, second important is also 0. Even though, that means even though your system has a dipole moment and everything is satisfying, but intensity is 0. Intensity 0 means as if it is a forbidden transition. So that's why it says, this line says that spectroscopic selection rules tells us only whether a transition may occur, but tells us nothing about intensity, which may accidentally be 0 or very low. So this is a kind of accident. On the top, the slope is 0, and so you have a very negligible intensity. Okay. So we are in the process of understanding this, how this fundamental band can have so many lines. Okay. So this is our aim now. For that, let us go back that what we are considering. We are considering a vibration of molecule. What is the spacing between the vibrational energy level? Is in 1000. 1650 is a ketone, and so 1000, in 1000. And if you remember the rotational spectroscopy, the B value is often 10 in the order of 1. So 10, 5, 6, 8. So rotational energy separation is this, where the vibration energy separation is this. So when you are talking about the bigger separation, obviously the smaller energy requirement processes also will take place. So when you are thinking of vibrational spectroscopy, actually vibrational spectroscopy will always have a contribution from the rotational transition. So we have to discuss the diatomic vibrating rotator. So both vibration and rotations are simultaneously happening. That is what we will discuss now. We did not teach you this rotational spectroscopy, but you know what is the expression for the rotational energy level, and now we have seen what is the expression for the vibrational energy level. So if you do it in wave number, so EJV, this is epsilon, J for the rotational spectroscopy, V for the vibrational spectroscopy. EJV is EJ plus EV without having any interaction term. Okay. So what is the EJ expression? EJ expression is BJ J plus 1 and then smaller terms. So this much here. Okay. And plus vibrational energy. Just now we have discussed vibrational energy considering anharmonic oscillator model. So just simple side by side we are writing. Now it says that you can consider D and H. D and H means this part you can consider, this term you can consider, eliminate, and this term also you can ignore. Why? Because D and H, their contribution is small. It is small in the sense that their numerical contribution does not affect your experimental results. Okay, like in experiment, most of the experiment case, IR your this resolution in instrument resolution, it will be around 4 wave number. So if their contribution is 4.0002, it doesn't matter whether you are considering this 0.0002 in this or not, because you cannot verify the experiment, because experimental resolution is up to 0.4 or 0.2. So this kind of things we are discussing about. But XC also you have seen that it is also a small number, 0.0147 or like that. Why you don't ignore XC? We are not ignoring XC, no? We are not ignoring. That reason is that XC directly affect you the fundamental band position, first overtone position. If you remember the expression, then omega E 1 minus 2XC. Okay, so it is directly affecting the fundamental band position. So that's why this XC should not be ignored, but you can ignore the HN. Okay, so if you ignore this one, then you will have a rotational component and then vibrational component, and the selection rule will be okay. So selection rule will be this one, this combination of vibrational one and the rotational one. And there is one rule that delta J plus 0 means that there is a change of the vibrational quantum number, but there is no change in the rotational quantum number. That is very rare case. Only few systems are there. These selection rules are there. Otherwise, it is the normal selection rule. So now we are in a situation to describe this one. So this is your, okay. So this is your potential energy surface. We are considering two vibrational energy level under the V is equal to 0. Another one is a V is equal to 1. So in vibrational energy V is equal to 1, you have several rotational energy level. In V is equal to 0, you have several rotational energy level. This rotational quantum number indicates the rotational energy level 1, 2, 3, 4, 5, 6, 7. Conventionally, the lower one is given in a double prime and the upper one is single prime. So now we are thinking of transition from one state, from one to another. So whenever you are talking about vibrational transition from one to another vibrational transition, then your rotational energy level also getting involved. That is what now we will be showing. So next one is taken from a Manuel book. It is looks like a bit complex, but it is not that complex. So if you see part by part, this one is the spectrum that appears. Just spectrum. Ignore the spectrum as of now. There are two parts in this. This is one part. This is another part. This one. Why two part? One part talks about the delta J plus 1 transition. Another part talks about delta J minus 1 transition. So one is minus 1, one is plus 1. And transition between the V is equal to 0, the rotational energy levels under V is equal to 0, rotation between rotation under V is equal to 0 to V is equal to 1. Okay, so follow wherever I am touching. So now we are in V is equal to 0, J is equal to 0 here. So now let us go, and where we can go from J is equal to 0 to the next one, where you can go? We are following delta J is equal to plus 1. So we can go plus 1. So this is the 1. So we are going to the 1. Next one, we started from j is equal to 1. This is, we start from 0. Next one, we start from j is equal to 1. So we will go to j is equal to 2. This dotted line means it's not up to the scale. Okay. So this can be this wide apart, this can be small. So that is the why dotted line. And the next one, j is equal to 2 to j is equal to 3 and so on. So these transitions, this transition follows this delta j plus 1. Okay. What about this one? What about this one? Now we have to think of delta j minus 1. Means if we start from 1 and then we will be going to the 0. Then it will be delta j minus 1. Q? Because 0 is the final state minus 1 is the initial state. Always final minus initial is the delta. So this is minus 1. So this is what given here. So every transition here minus 1. This is minus 1. This is minus 1. So every transition is minus. So these transitions are, now let us see what happens in the spectrum side. Now this is the spectrum. There is a line here. There is a line here. This means there is a line that is not okay. So this is the transition spectrum. Now there is no transition between 0 and 0. Okay. Rule delta j 0, we have said that it is usually not happens, because whenever there is a change in the delta v, delta j must change, except some specific cases like nitrous oxide. So this center band is not there, so there is no band here. Now this band, this transition appears here, this transition appears here, this one appears here, appears here. So this side of transition is known as R branch. If you follow this one, this energy level is going this way. If you follow this one, that energy level I am thinking all the time is right hand side, then you can remember this branch as a R branch. This is known as R. You can think right side R, right hand R, provided you are plotting it this one. Maybe I have that. In some book it will be just opposite. There you will see this is also opposite, that is that direction. So this is R branch. Then how the naming happens? R0, R0. Why 0? Because it starts from 0. So next one, it starts from 1, so it is R1, R2, R3. Now this is P branch. R, and there should be, if there is a band here, then it will be Q. So P, Q, R, at least a sequence is there. So delta J plus minus 1, P, Q, R. In case of Raman, you have a plus minus 2. So this time another letter, previous letter, P ke pehle O, O, and this is R ke baad S. So that will be, Raman will be giving O and S. So here we are getting P branch and R branch. And in P branch also you see this P starts from P1, because originating start state is 1. So we start from 1, so it gives you P1. Similarly P1, P2, P3, P4 and so on. So अभी तक ये ठीक है? So now our proposition, whatever we are thinking, that there is involvement of rotational energy level. So this fine structure is because of the transition from one rotational energy level in V0 to another rotational energy level V1. That is why you see this line. So this is actually this is the fundamental band. So is it everything? Okay. Then we have to get an expression for that. What is the expression? Expression development is very easy. V is equal to 0 to 1 only you are considering. So you will have an expression. After this expression, You have to consider two scenarios. One is delta j plus 1, another is delta j minus 1. So delta j plus 1 considered, you get expression omega 0 2b j double prime plus 1 minus 1 minus 2b this one. These are the very simple thing. There is no derivation, nothing. So you have two expression, this one and this one. These two expression you can write in a common way, omega 0 plus 2bm. So 2b is there. So this one m means, m in first case is j double prime plus 1, here m in this case minus j prime plus 1 m. So if m is this thing, so your expression is omega 0 plus 2bm. Now m can be plus minus 1 plus minus 2, but m cannot be 0. Why m cannot be 0? If m is 0 here, then j double prime, the rotational quantum number is becoming minus 1, which is not possible. So m cannot be 0. If m cannot be 0, then in this expression omega 0 plus 2b, the 2b will be always there. You will not have any situation where you will see the center of the band. So center of the band comes at omega 0. Always you will have either 2b plus or 2b minus, because m is not 0. Okay. So this expression, if you are considering this d term or h term, then it become omega 0 plus 2bm minus dmq. Otherwise, this is the simplest example. This expression is called combined vibration rotation spectrum. So you can use this expression and get that former spectrum. How? This is the center position, this is the center position. Now m is equal to 0, not possible, so center mein no band. M is equal to plus 1, omega 0 plus 2b, omega 0 plus 2b. 2, omega 0 plus 4b, omega 0 plus 2b plus 4b, means here. 6, here. That means these lines are spaced 2b, 2b, 2b. That side also minus, 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 2b, 2b, 2b. So what we are getting now? These lines, this one R branch, this is P branch, P, this is R. Every line is equally spaced, 2b, 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 2b. Center is not same because m cannot be 0. So between this is 4b. And this is already I have told you. Okay. We are happy that we could explain that so many lines. But again, if you do analysis with other molecule under a same molecule under a high resolution spectroscopy and then see the data. So see the data P, P1, P2, P3, P4. This is taken from another book. So difference between P1 and P2 is the 2b, 3.88. Difference between P3 and P2 and P3 should be again 2b, so it should be 3.88. Difference between this again should be the same, but you see there is a change. 3.88, 3.92, 3.95, 3.98 means difference is increasing. Difference is increasing. Where difference is increasing? In P. In P branch, whatever the difference here, that is different than whatever the difference here. Okay? So it is not same to B. Again the problem is R branch. R branch, let us see. R0 appears here, R1 appears here. So difference between R0 and R11, 3.78. Difference between R1 and R2, not 3.78, 3.73. Difference between these two, again decreasing, again decreasing. So this side it is decreasing. This side says that it started here 3.78, difference between these 3.78, and difference between 3 and 4, 3 and 4, 3 and 4, this is 2, 3, 3 and 4. This is 2 and 3 and 4 is 3.66. That means whatever you are proposing is not correct, is not able to describe this one. Then again you have to think, where is the problem? When is the time? Yeah. Please. So now we have to think what went wrong. So there, if you remember that when we are deriving that equation, this one, in this is V is equal to 1 state, this is V is equal to 0. But that means you have V is equal to 1, under the V is equal to 1 and under the V is equal to 2. So these rotational states, their rotational quantum number we have taken B, and here also rotational constant we have taken B, here also we have taken B. Means even if there is an increase in the bond length, but that is not changing the B value, which is not possible. So we have to consider now that B changes. So that means Born-Oppenheimer approximation is invalid. If you consider Born-Oppenheimer approximation is invalid, then you have to consider the B for V is equal to 1 as a B1 and B for V is equal to 0, this one as say B0. So if you now do the same thing, do the same calculation, only consider that when you are considering that V is equal to 1, then you write B1. When you are considering V is equal to 0, then you are writing B0. Then if you do this one, if you do this one, so V is equal to 1, so B1 minus V is equal to 0 minus B0. That's all, or nothing else. Then if you do, and then if you do the same way, the final expression will be final expression is, last time you had omega 0 plus 2bm, this time you have omega 0 plus b1 plus b0 m plus b1 minus b0 m square. Now whether this relation is correct or not, you can check it. Now think b1, think of think of that B1 is equal to B0. Born-Oppenheimer approximation is valid. There is no change of rotational constant with the vibrational energy level. B1 is equal to B0. So B1 is equal to B0 means this term vanishes. Then it becomes 2Bm. Now this combined expression, if you see, then this will allow you to explain the spectrum. This one will allow you to explain the spectrum. This will be your homework. Okay? Use this expression to understand why there should be a decrease in the spacing between the R branch and increase in the spacing between the P bands. Okay? So use this expression to explain this CO gas molecule spectrum. So this CO gas molecule, as I said, that the spacing between the P branch between the bands in the P branch is increasing, and for the R branch it is decreasing. Okay, so this you have to explain with the help of that expression that you have just seen, this one. Okay, I think we are running out of time, so this might be the last one. So where we have started, this is the evolution of this spectroscopy. We have started with the harmonic oscillator model, and then we saw that only one band is expected, omega OSC, which is not enough for the multiple bands. So we then changed our approximation. We now consider, instead of harmonic oscillator, we consider anharmonic oscillator, which allows you to think the bond breaking event. So for that anharmonic oscillator, and the energy level is also, energy level expression is changing from half kx square parabolic expression to the Morse expression, and that's why you get a different expression for the energy level for anharmonic oscillator model, dielectric model, and this is the different expression. So now this one allows you to get multiple band, fundamental band, first overtone, and so on, but this doesn't allow you to explain the lines appearing in the fundamental band. For that we have to consider the vibration, rotation together, and for when you are considering Born-Oppenheimer approximation is valid, that means there is no change of B with the change of vibrational energy level, then we get this expression. This expression allows us to think of appearance of line having an equal space, but when you see the high resolution spectrum of CO, then you see it is not equality not maintained. In R branch and P branch, their trend is different. In one case it is increasing spacing, another case is decreasing. Then you have to think of the Born-Oppenheimer approximation is not correct. So breakdown of Born-Oppenheimer approximation, then you get a different expression, and that one allows you to explain the CO molecule. This is how things happen. This is simplest example, and everywhere in the science it happens. You start from the lower one and then keep on rectifying it. Okay. So I am supposed to teach you this instrumentation also. Instrumentation, maybe tomorrow sometime we will be touching it, instrumentation. Okay. So if there is any question, then we can handle it in next session.